Alright, before spring break we started the section of notes called Properties of Logarithms. We talked about exponential functions and logarithmic functions and how they related to each other. So I'm going to let you go back and look over your notes that we took in class. We talked about the inverse property, we talked about the product rule and the quotient rule, and we're just going to pick back up where we left off looking at the power rule. Alright, so the power rule states that if you have a log where everything inside of that log, say the input, is all raised to the same power, then what we're allowed to do is to take that power and take it off of the input and multiply it times the front of the log. So for example, if I have log base 9 of 5 to the x minus 6 power, everything inside of that log is raised to the same power of x minus 6. So everything, all of the input is raised to the same power. What the power rule says is that we are allowed to multiply that power out front of the log. So it becomes x minus 6 times log base 9 of 5. Now you'll notice that I put x minus 6 in parentheses, and that's going to be significant. Later on we might want to distribute into the parentheses if we wanted to. We could write that as x times log base 9 of 5 minus 6 times log base 9 of 5. So it's important that you put the exponent in parentheses when you bring it out to multiply it times the front of the log if that exponent has more than one term. So in this case, since it has two terms, it needs the parentheses around it. Now we can actually just stop right here, that would be good enough. But we do want to have the parentheses just in case at some point in the future we might want to distribute that log into that parentheses. Alright, log base 7 of the square root of x. We can write square root of x as an exponent when we have an index on a radical and we have a power on the input. One of the things that we want to do before we start using the power rule is to convert radicals to exponents. When we convert radicals to exponents, it's always the original power that's on that base divided by the index power. This number that sits in that little V-shaped portion of the radical is called the index. So we're going to convert radicals to fractional exponents. The power that's on that part underneath stays as the power goes on top of that little fraction. The index becomes the denominator of that exponent. Once we have rewritten the radical as an exponent, now we have all of the input inside of that log raised to the same power. The power rule then says that we can multiply that power out front of the log. So the key here is that we always convert radicals to fractional exponents. Alright, our next example, we want to be careful when we use the power rule that we use it correctly. Here this says that all of that power must be raised to, all of that input must be raised to the same power. Here that 4 exponent only applies to x, the 5 only applies to the y. So we're not actually allowed to use the power rule unless all of the input is raised to the same power. Can't bring the 4 out to the front or the 5 out to the front. So the only thing I could do now is to recognize that I'm multiplying in between. And so I'm just going to scoot up here and remind ourselves of this rule that we have. The product rule says that if you are multiplying in between two quantities inside of a single log, that you can actually separate that into two logs where you're adding in between. So I'm going to use the product rule, and then I'm going to use the power rule. So I'm going to use the product rule to write this as log base 7 of x to the power of 4 plus, so multiplying in between two things inside of a single log gives us adding in between two logs of the same base. And in the second log I'm going to put y to the power of 5. Now when I look at each of those two separate logs, I have now all of the input in the first log raised to the same power. And in the second log I have the same thing. I have all of that input raised to the same power. So I can actually now use the power rule, and I can bring that 4 out multiplied times the front of that first log. And then the second log I can bring the 5 out to be multiplied times the front of that second log. Our last big property that we're going to talk about is called the change of base rule. I like the change of base rule. Typically on a standard graphing calculator, you wouldn't have a log of any base. You would have only log base e and log base 10. So if I wanted to put, let's say for example, log base 7 of 9 in my calculator, I would not be able to put that into a standard calculator. Now there are some calculators that will let you do that. However, you might be on a test at the University of Houston where they don't let you use calculators, and then you might have to do something else. The change of base rule is just a really nice rule. It gives us a lot of versatility. The change of base rule says that if you have a log with some base, we'll call that base A, of some input, that you can actually rewrite or change the base of the log. You can rewrite that into a log of a different base. So you would write that as log of some base b of the input, and then log of the same base, so both of these logs on the top and the bottom of that fraction have to have the same base, and then what goes inside of that bottom log would be the base. So how does this look? Well, so for example, if I wanted to change log base 7 of 9 into a different base besides 7, I could rewrite this. Let's say that I want to rewrite this as log base 10. I would have to have log base 10 at the top and the bottom. And then what would go at the top then, into the top log would be the 9. What would go into the bottom log would then be the 7. If you had a standard calculator now, you could actually put this into your calculator and figure out approximately what that was. I want to show you how to do this using DesMOS if you don't have a graphing calculator at home. So I'm going to pull up a website called DesMOS. So DesMOS.com. This will allow you to do almost everything that a graphing calculator would do. So I'm going to go to that, and I would recommend that you do that as well, and you would be allowed to use that for an exam. So I'm going to go there, I'm going to click Start Graphing, and I'm going to recall what we were looking at, log base 10 of 9 divided by log base 10 of 7. Okay, so we're going to go to the little calculator, the little keyboard at the bottom left, and I'm going to go to Functions. And we're going to click through. This is the trig section. I have what we call a stat section, distributions, and then we're going to go to miscellaneous. You'll see here we have log, that's log base 10. This is ln, that's log base e. This would give you the opportunity to do log of any base that you wanted. That is not standard on typical calculators. So I'm not going to use that, I'm going to use this. we're going to do log base 10, and we said, what did we say, 9 over 7. Okay. I'm going to put in a 9. Then I'm going to say divided by. Then I'm going to go back to functions and miscellaneous, and then we're going to do log base 10, divide that by 7, and then you see that you get the approximation for that. So we're going to round, I'm just going to round to the nearest 3 decimal places. So that would be 1.129. So what this allows us to do is, if we wanted to figure out what is log base 7 of 9, I could actually convert this using my change of base rule into logs that are on a standard calculator, and then I could find that approximation. We can also use the rule going backwards. Let's say that you have a log of the same base at the top and the bottom of a fraction. You could actually convert this into a single log. The top of the log, the input there would be the original input of that one log. So just to be clear here, I am going to go back to our rule. So what we have in example M is we basically have the right side, and we are looking to move to the left side. So we have 2 logs of the same base, and I want to smush this back into a single log on the left-hand side. So it's going to be log. Now we want to keep in mind something here when we go backwards. This x, this is the input of the top log, it becomes the input of that single log. So the input here would be 15. That's the input of that single log on top. So the top log, that input would become the input of that single log. When we look back at our rule, the input into the log in the bottom, that came from the base of that log on the left-hand side. So the 91 would correspond to the input in the bottom log, and therefore will correspond to the base. So you can go back and forth between the left side to the right side, or the right side to the left side, depending upon what you're given. That rule works both ways. Okay. And I really like example N. It's one of my favorite problems. This makes a good test question. Log base 2 of 6 times log base 6 of 8. Now one of the things you might be tempted by is this multiplication. I want to go back and I want to look at my rules that we've accumulated so far. We have the inverse property that says if the base of the log and the base of the exponential match, they cancel each other out. We have that if we're adding in between 2 logs, we can combine them into one log. There's our product rule. We have if we're subtracting between 2 logs, then we can combine that into a single log. And then we had our power rule. For example, N, we are multiplying in between these 2 separate logs. We actually don't have a rule. We have not come up with a rule yet that tells me what to do when I'm multiplying in between 2 single logs. We also notice that these do not have the same base. So we kind of have 2 strikes against us for this problem. What I'm going to do is I'm going to go ahead and convert both of those logs into a log of the same base. The log property, the change of base log property here, doesn't tell me what the original base of the log has to be, and it doesn't tell me what base I have to convert into. I can convert into any base I want. So we don't have any restrictions. I could convert this first log. I could convert that into log base 7, log base 12, log base 11, whatever log I want. Now I'm just going to go with natural log, log base E. So I am going to take this one single log and I'm going to rewrite this, changing the base of the log. So according to my change of base rule, moving from left to right. So I'm going to rewrite that as 2 logs of the same base, one on top of a fraction, one on the bottom. What would go into the top log? And that'd be 6. So the original input becomes the input into the top log. The base, the original base of that single log, goes into the bottom input. Okay. We're going to multiply that times. Now I'm going to use change of base rule for the second log, and I'm also going to convert this to natural log. Okay, what would go into the top of that log? Well, that would be the original input of that single log, and the bottom is the base. So the base goes at the bottom. Now I've converted those into both of those into logs of the same base. They're all natural log, which is log base e. One of the things that I noticed as soon as I did that is that the top of this fraction is identical to the bottom of this fraction. So those actually can cancel each other out. When I cancel things, I'm actually leaving a 1 behind, because anything divided by itself is 1. So now when I multiply across, now at the top, 1 times natural log of 8 is natural log of 8. Natural log of 2 times 1 is natural log of 2. Now I could stop and put that into my calculator very easily, but I'm actually going to go a little bit further just because I like to. I actually noticed that now I'm actually on the right side of this change of base rule, where I have two logs. So if you look up here, I have 2 logs of the same base, natural log of e, natural log, log base e, and I'm dividing in between them, and so actually now I can convert this into a single log like we have up here on the left of that rule. So if I do that, the top input becomes the input of this log. The bottom input now becomes the base of this single log. Okay, and I can actually do this whole entire problem without a calculator, which is really nice, just using my change of base rule. So if you remember, before spring break, one of the first things we talked about is how to evaluate a log. What does it mean? We talked about something called the exponential form. The exponential form would be to take the base of the log, write it big, raised to what exponent would give you to the input of the log. And so if I do that here, the base of the log is 2. 2 to what power would give us to 8? So 2 to what power would give me to 8? The answer would be 3. And the answer that we get for a log is always that required exponent. So after all of that, without a calculator, I'm able to get all the way to a simplification of just 3. Alright, the last part of log properties is talking about using all of those log properties that we talked about to expand and to condense. The first thing we're going to look at is using properties of logs to expand the expression and simplify. When we say expand, we mean to use log properties to go from one log to many logs. The goal is to use log properties as much as possible to rewrite input of all the logs so that no log has a power, no log has a product, and no log has a fraction. So the first step is to rewrite all radicals as exponents. Then we are going to use the product and the quotient rules. We're going to talk about how to do that all in one step. And then we're going to use the power rule last. So the first thing that I'm going to do with this log is I'm going to rewrite the radical. So here we have a radical. We have that radical symbol, that cube root. That's called a radical. The index of that radical is 3. The first step is to rewrite all the radicals you see as exponents. And it's always power over index. So the index of this radical is 3. So at the top, I'm actually going to write that as x squared plus 1. That's everything underneath that radical. And we're going to say that's kind of an implied power of 1 there. And then we're going to write the bottom of that fractional exponent as the index 3. So anytime that you have a square root, that's going to be like, let's say square root of x, that's going to be x to the 1/2 power. If you have cube root, let's say of x, that would translate to x to the 1/3 power. Okay, so the first thing we're going to do is any radical that we see, we're going to convert those to fractional exponents first. Okay, so there's our first step. The second thing that we're going to do is we are going to use the product rule and quotient rule all at the same time. So this is a really nice and really easy way of doing this process. Any factor that I have at the top of the fraction is actually going to go into a positive log. So when we look inside of this one single log, we're going to stretch this out into multiple logs. Anything in the top of the fraction is going to go into a positive log. Any factors that are at the bottom of the fraction inside, so any factors at the bottom of the fraction, are going to go into a negative log. So let's see what we mean here. We're going to say this is equal to, now when we stretch this out from one log to many, we're going to keep the same base. So it's still log base 5. And inside of that log, we're going to put x to the 1/2 power plus x, all of that raised to that 1/3 power. So that input is going to go into a positive log. When we say positive log, we mean that the number out front of that log is positive. So we're going to kind of assume that's like an implied positive log base 5. So the sign out front of the log. Now the other two factors are multiplied together at the bottom of that single fraction inside of that single log. Those are going to go into negative logs of the same base. So negative log base 5 and then negative log base 5. So when we say negative log, we mean that the sign in front of the log is going to be negative. So things that are multiplied together at the bottom of that single fraction are going to each go into their own logs, but they're going to go into negative logs. Okay. The last thing that we use when we're expanding is that power rule. We're going to bring all powers to the front of the log if possible. The only way that that is possible is if everything inside of a log is raised to that exact same power. So in the first log that we have, everything inside is being raised to the 1/3 power. So we are allowed to use the power rule to multiply that 1/3 out to the front of that log. There are no other powers, so there's nothing else we can do with the power rule. We'll just copy the rest of the problem down. Okay, so this is expanded as much as possible. Now you might ask why we haven't brought out this 2 to the front of the log. And the reason why is because the power rule says that all of the input inside of that log has to be raised to the same power. But that exponent of 2 only applies to the x, it does not apply to the plus 1. So we're not allowed to bring that 2 out to the front of the log. So we do what we can as much as possible. And then if there's a power that we can't bring out because it doesn't follow the rule, then we just have to leave it in. Alright, let's look at another example of expanding. So now we have natural log, and we actually have 3 things inside that are multiplied together. We have 5 times x squared times the square root of x, the square root of 1 minus x. And then we have divided by, and then we have 4 times, and then we have x minus 1 squared. So we're going to take anything that's at the top of the log and anything that's at the bottom of the log, and we are going to separate them out into positive and negative logs. Before I do that, I notice that I do have a radical. So I am going to rewrite square root of 1 minus x as 1 minus x to the power of 1, but remember the index 2, that number that's in that v-shaped portion is called the index that goes at the bottom of that fractional exponent. So now that actually becomes 1 minus x in parentheses there raised to the 1/2 power. So that's what I'm going to do first. I'm going to rewrite any radicals as fractional exponents. And now anything that's at the top separated by multiplication is going to go into a positive log. So I'm going to have positive 5, so natural log of 5 plus natural log of x squared plus natural log of 1 minus x to the 1/2 power. So anything that's at the top of that log separated by multiplication, so all those different factors go into positive logs. Anything at the bottom of that fraction then is going to go into a negative log. So you'll notice that we started out with ln, and I'm going to use ln for all of the logs as I separate this out into multiple logs. We'll put a 4. So we have 4 times, there's 2 factors down there, and we have an x minus 1 quantity squared. So anything multiplied together at the bottom of that log is going to go into a negative log. So each factor gets its own log, but they go into negative logs. So that's really important. The last thing that we do is we bring out any powers that we can. So here I have all of my input for that second log raised to the power of 2, so I can bring that power out to the front of that log. For the third log, all of that input is raised to the power of 1/2, so I can multiply 1/2 out front of that ln. Here there's no power to bring out. On the last log, everything inside is being raised to the power of 2, so I can bring that 2 out to the front of that log. So it becomes negative 2 natural log of x minus 1. And that is the expansion. Alright, our last example of expanding. We have natural log, we have a fraction, and what we notice here is that that fraction, everything is raised to the power of 3. So one thing that I could do here, and I could do this a couple of different ways, I would be allowed to actually bring that 3 out to the front of the log now if I chose. There's no radicals this time, so I don't have to worry about that. So 3 times the natural log of that fraction. Now I can take what's at the top of that log and put it into a positive log, so ln of 2x plus 1, and then anything that's at the bottom of that log is going to go into a negative log, so negative ln 3x minus 5. And I can choose to leave it exactly like that, that would be fine, or if I wish to, I could take that 3 that I brought out using the power rule and I could distribute it. So that would look like 3 times the natural log of 2x plus 1 minus 3 times the natural log of 3x minus 5. So that 3 would stay out front of the log when I distributed that 3 to both of those logs. So that's using our power rule to expand. The last one we're going to look at here, we're only going to really look at one of these because these are not too bad at all. A little bit simpler even than expanding. We're going to look at using our power rule to condense. So condensing means that we're going from many logs to one log. We're actually going to do exactly the opposite of what we did for expanding. The first thing that we always look to do is to use our power rule. So we're going to use the power rule first. Any value that's multiplied out front of the log is going to be put back on as the power on all of the input. So I notice that I have a a 3 out front of that log. I have a 2 out front of that log, and I have a 1/2 out front of that third log. So any value that's multiplied times the front of the log is going to be put back on as the power on all of the input of that log. So the first thing I do when I condense, go from many logs to one log, is I'm going to put those numbers out front of each log back on as the power of the input on all of those logs. One thing I do want to mention is that when you do take many logs and you convert them into one, they do all have to have the same base. So that's kind of implied here. They're all natural log, so they're all base E. So just to make sure we have that down. Okay, so I'm going to move this to the power on all of the input, move this to the power, and move this to the power. So what we have now is natural log of 3x plus 1, all of that raised to the power of 3, minus natural log of 2x minus 1 squared. Now you'll notice that I left the negative. I never take the sign and put it as a power. Typically we prefer to have positive exponents, so I'm just going to leave the negative. I'm just going to take the number as the power. So that last one becomes negative natural log of x raised to the 1/2 power. So the number itself doesn't change, it just becomes the power on all of the input for that log. The next rule we're going to do is our product and quotient rule together again, all inside of one step. So anything that's inside of a positive log is going to go at the top of the fraction. So this isn't a positive log. When we push all of this together, remember we're going to push all this together into one single log of the same base. Anything that is inside of a positive log, so the first log is positive, that's going to end up going at the top of that fraction on the inside of that one single log. Anything that's inside of a negative log, so we have two negative logs here. Anything that's inside of a negative log is going to go at the bottom of a fraction of the fraction inside of that single log. And everything, and I'm going to circle this here, they get multiplied together. So if you have two things inside of a positive log, or two things inside of a negative log, or three things, all of the pieces that we have that go at the bottom of the fraction are going to get multiplied together. So it looks like this. 2x minus 1 squared is in a negative log, so it goes at the bottom of the fraction. And it's going to be joined together by multiplication to anything else that's also in a negative log. So that becomes times x to the 1/2 power. So anything inside of a negative log just automatically gets multiplied. So not added or subtracted, but multiplied together at the bottom of that single log. Now if you want to, this is optional to me, but if you wanted to, you could go back and convert any fractional exponent back to radicals. Here we go. So this is optional. I don't require this, but if you have x to the 1/2 power, you could rewrite that as the square root of x. I like this answer, and I also like this answer. Either one of those is perfectly fine to me.